Very happy to see you all here. So today we have the chance to have a webinar from Professor Patricia Hidalgo-Gonzalez from the University of California, San Diego. She'll be presenting her recent work on learning to control in power system design and analysis guideline for concrete safety and problems. So let's start with a 45-minute give or take period, and then we'll open the floor to question. So the floor is all yours, Patricia, and yeah, let's enjoy your talk.
All right, thank you, Antoine, and thank you so much for inviting me and for having me in your seminar. I'm super excited to exchange some ideas with all of you. So as Antoine said, I'm an assistant professor at UCSD in the Mechanical and Aerospace Engineering Department, and I'll be talking about one of our recent papers that's at the intersection of learning or like using machine learning techniques for controlling power systems specifically. So I'll split the talk in a few sections. First, I'll introduce the space and what we are basically proposing to the community that we can start doing or being mindful of as we're using this type of techniques in the context of controlling power systems. And then I'll talk about one specific case study that we have in the paper. In the paper, we have two case studies, but I'll focus the one on frequency regulation, which comes particularly from my work. And the second case, it's an OPF that comes from my collaborators, but you can check that out in the paper if you're interested. And I'm going to close with some guidelines that we're proposing on how we can address these safety issues that arise when we're using these data-driven methods in the context, again, of controlling power systems. So I make emphasis on controlling because we could use data-driven methods in different contexts, for example, in state estimation or forecasting, clustering, classification. But here in this talk, I'm going to be focusing specifically when we're deciding how to make a decision. So specifically for decision-making or controlling different variables in power systems. Right, so we've been seeing that there have been several new learning-based strategies to control dynamics in different areas of power systems. And these developments, they have been great in terms of performance. Now we can operate things more efficiently, and with all the data that we have incoming now, we can do a better job than what we could before, especially as we're transitioning towards having a higher share of renewable energy. But then on the other side, or the other side of the coin, is that given that we're using now these data-driven methods, they bring vulnerabilities and safety risks that we didn't have before when we were only doing like model-based approaches or engineering approaches in the classical way that we used to think. So mitigating these new vulnerabilities from using these machine learning techniques requires extra analysis and design, which sometimes tends not to be done in this intersection, and we need to start doing that more and more. And there are many examples in this space, and in particular, in this paper that I'm basically talking about today, we do have a large section where we go over the different domains in power systems where these learning techniques have been used for controlling different actions in different contexts, for example, frequency regulation, voltage control, OPF, demand response. And there we look at those contributions from the critical lens on one hand, what are the contributions of now using these methods instead of the classical methods? But then on the other hand, looking at what are now the new vulnerabilities and aspects that are arising from using these data-driven methodologies. So now let's review what are these risks that I'm mentioning. And from here, we take some of the language and concepts from the AI community, and we apply them to power systems. Specifically from the paper from Amodei and their co-authors, and also Like and his or her co-authors, they characterize specific safety concerns that arise as they're working, or as we're all working in learning-based control, and we apply them to the context of power systems. So the first one, it's avoiding negative side effects. So this comes from the fact that when we're using a machine learning model, it's optimizing the actions according to some objective function that we define and some constraints that we define. And usually that's going to be informed from the expertise of the domain in particular that we're applying this technique to. However, given that we can only choose an objective function with a certain characteristics or design, and the same for the constraints, we will never be able to capture all possible behaviors of our physical system. And that could bring some aspects of getting into an area that we haven't explored, that we were not able to model with the constraints that we have. So then that makes our algorithm not to be robust, no matter what's happening. And then the other risk that's super important when we're looking at machine learning techniques in the context of control for power systems, is to make sure that we're doing persistent excitation and safe exploration. So the question that this is posing is, how can we make sure that the training data that we're either obtaining or creating represents all the possible conditions that we could be under, especially the safety critical cases? And this question comes particularly, or become particularly relevant when we're looking at using historical data for a few different reasons. On one hand, historical data is data usually where a certain system was operating, and it might have some data points where the system was in a more critical case, but generally it's not rich of that type of cases. So then when we're adapting or training an algorithm to learn from that type of historical data set, it might be biased towards knowing what to do in the case of normal operations rather than being ready for a more safety critical case, given that the training data was enriched in that type of cases. So we need to be mindful of that. And similarly, if we start working with hybrid data sets, meaning some historical and some synthetic, we need to make sure that on one hand, the synthetic data set is not getting biased because of our modeling approach. And also we can leverage that approach by creating these safety critical cases that we wouldn't be able to get from the historical performance. And then the other aspect of now safe exploration, it's, for example, when we're doing online learning, the question would be what safety mechanisms we have available so we can prevent unsafe exploration scenarios. So towards the end of the talk, I'll touch base a little bit on this. But for now, I'm just introducing it. All right, and another safety risk that we see also in the context of power systems is robustness to distributional shift, or basically what happens when we have a distributional shift and how can we design robust mechanisms against it. And this comes from the fact that the environment, it's going to change. Power systems are changing as time goes by. For example, if we're looking at the distribution network, we could have new appliances connecting or disconnecting in the different homes. And then we could also have the topology of the network to be growing if, for example, more development is happening in a certain neighborhood and the city is expanding. So we are expecting our environment to change. So then the question becomes, how do we make sure that this machine learning model that we might have trained is able to recognize this change and can also adapt to that change and still be able to perform in a good way or in the way that we intended it as we start experimenting with now a new environment. And then the last aspect related to this is how do we make sure that the model's own control actions don't cause that distributional shift in a way that it harms the operation that we have. So what this means in particular, let's say, for example, we've seen in some cases when you have an OPF problem and you're trying to mimic the OPF optimal decisions, but from the perspective of using a machine learning mechanism or algorithm, and you have to choose different features, right? And let's say that you use some of the endogenous features, for example, such as the voltage at a certain node, you would like to use that as an input feature to then predict what should be the reactive power injection, for example. So in that case, because you're using the voltage at that specific node, you're using data that originally might end up shifting your behavior and might move basically your state space, your operational space to a space that you were not trained for, given that you're using this endogenous variable. So it can get a little tricky, and there are ways around that, but one needs to be mindful on how you're going to use your input features in a way that it doesn't drive you away from the behavior that you were trying to mimic. And there's an example of this in the paper as well. Then due to time, I won't be able to cover it, but that was like the sneak peek that I just gave. But if you would like to look into more details, definitely take a look at the paper where we show that case study. And last but not least, here in power systems, we're working with a legacy system. And that brings a new set of challenges, which other type of domains don't have to deal with. For example, in robotics, when you are implementing machine learning algorithms to control for example, your motion or path planning, you don't have to make sure that your controllers are compatible with a pre-existing machine, because you're basically modeling from zero, you're creating a new device. But in the case of power systems, that's not the case. We are now bringing new controllers, but to an existing grid. And in many cases, that network has been operating for over 100 years. So it has a lot of different layers and aspects. So we have to make sure that any new control mechanisms that we bring are complementary and interact well with the control mechanisms that we already have in place in the grid. And in that regard, the other aspect is that as of now, the expert in the room, it's always going to be a human. So we need to make sure that the human operator can safely override any of the control mechanisms that we might have, especially if you're getting into safety critical aspects that you don't expect the controller that was designed to work in the best way or better than a human, the human experience would know. So we have to be able to design these mechanisms in a way that the operator can take over if needed. All right, so now that we reviewed these different safety risks, let's look into one case study that's looking at frequency regulation as inertia changes over time because of renewable energy integration. And then I'll go highlighting what were the safety risks that we identified and how we were addressing them with this case study. Okay, so as we know, we need to balance supply and demand at all times to maintain frequency at the operational point that we want it to be. And if we don't do that, we're risking a blackout. And there are several cases by now. And one example was the one in Australia back in 2016. And now looking a little bit more at the dynamical response of what happens when we have such an event where we're not able to meet supply and demand at a given time point. So here in the y-axis, we're looking at frequency. Then 50 hertz in this example was the operational point. And then on the x-axis, we're looking time or how the system is evolving over time. So in this case, we had an incident in this point, and then frequency starts dropping. And this initial response or the derivative at which the frequency is changing, it's given by the inertia of the system, which I'm going to briefly explain in a couple of slides what that is so you can get the physical interpretation. And after that, immediate response, which is just a response from the differential equations that are governing frequency in that moment of time. Then we have different control mechanisms that kick in, such as the primary control. Then the secondary control takes over and relieves the primary control. And then we have reserves that start kicking in, and then we start redispatching. So then we can free these different units that we're providing, the primary control, secondary control, and then we can just rerun our OPF so we can have the generators provide and adjust to this new change. So now looking into a little more details on what's happening with frequency and why it can deviate depending on what's happening with our supply and demand. This is what's called the Swing equation, and it's a simplified model for modeling frequency in a network. And in this case, we're modeling with delta F, the change in frequency from our nominal point. And here we have the derivative, and here we have just delta F. And as you can see, it's a linear system. And I want to highlight a few terms over here. So there are a few constants, which are all of these over here, and I'll touch base on some of them. But the state variable that we have, again, to reiterate that, is the deviation in frequency. And then its derivative, of course. And now the terms that I want to draw your attention, it's P and V. So P and V, they're representing P, it's the injection from the generators, and D is the demand that we are experiencing at a given time point. So let's say that frequency is not changing and we are operating at the nominal point. So if we have no change, this delta F would be 0. And these terms over here are constant, just constants, then multiplied by 0, that goes to 0. Then if our power injected, it's exactly the same as the demand that we're withdrawing, this term would be here, 0. And if we're doing nothing with the control action, this whole term would be 0. So in the end, our derivative of the change of frequency would be equal to 0. So nothing would happen and we would continue operating at the nominal point. So that's what we want. But then in which way would it deviate from it? For example, if for some reason our demand drops suddenly and we're injecting more power than the demand that we are drawing, now this term of the power injection minus the demand would be positive, and then multiplied with this constants that are also positive would be positive as well. So that would mean that the derivative of our frequency would have a positive sign. So our frequency would increase when we're injecting more power than the demand that we have. So that's how our frequency starts deviating anytime our demand is not matching our power injection and vice versa. And the other term that I want to draw your attention to is this constant M. It's called the inertia constant. And this is basically the kinetic energy that the generators have, the ones that have like spinning turbines, over the rated power. So one example, for example, if you're looking at hydropower, you have your turbine spinning, and that has kinetic energy from that movement. And if that energy that you have in your turbines from spinning masses, you would divide it over the rated power of that hydropower plant, that would give you a number of seconds. And that number of seconds, what it tells you is if you would stop providing fuel or water in that case, for how many seconds would you be able to continue providing the same amount of power, given that you don't have more fuel or more water in that case, from just extracting the energy that you have in the rotating masses. So that's the concept of inertia from generators that have spinning turbines. So back in the day when we didn't have much renewables on the grid, we could think of the inertia in our systems to be constant because our electricity mix was basically dominated by coal, natural gas, that they have all like high inertia constants, even nuclear power, it has a high inertia constant, hydropower. But now, as we have renewables, we're seeing this shift away from that constant paradigm, because now depending on the time of the day, we can get a different electricity mix providing or supplying our demand. And the way that we can estimate this inertia constant in a network, it's basically you have all the generators that are online, and you could take like a weighted average of the inertia constant that each of them are contributing with in the grid. So when we had a more thermal power type of network, this was basically a constant, no matter what time of the day it was, because you had the same electricity mix providing electricity at any time of the day. But now that we have renewables, things are changing quite a bit because, for example, solar power and wind power classically don't provide any inertia in the grid. So when we're in hours of the day, when we have more of those resources providing electricity into our grids, the inertia or that weighted average gets closer to 0. And this is an example that we were looking at in Germany. So in the y-axis, we see that aggregated value for inertia in the German grid. And in the x-axis, we see time every 15 minutes. So even though this data was from back in 2012, even then they were already starting to see that inertia was varying quite a bit and also getting pretty low in some cases. So now what we had before, where we were assuming that this term M was going to be fixed, now we cannot do that anymore. So now we're not working anymore with that linear system, but we're working with something a lot more complex. And here's just an example of what would happen with the frequency response in the y-axis and x time, as we have different values for inertia. So when we have a higher value of inertia, it's basically providing more resistance in the grid for frequency to deviate. So then the delta F1 in this example, it's smaller than delta F2 when you have a lower inertia in the grid. And in this other example, it's from ERCOT. So also, even though this is data that they had from 10 years ago, in one of their reports, it was already showing that for a given power loss, now in a difference of 42 years, they could see that the change in frequency was increasing quite a bit, even though they were experiencing the same power loss. And that was explained because now they had more wind power, so therefore less inertia in their system. So this brings me to the research gap that this case study was addressing. And most studies have been focusing on controller design for a few values of inertia, but they were assuming that the dynamics were time invariant. So basically assuming that inertia was constant, and then they would test it for a few different values. And in previous work, we were able to design via learning a fixed and stable frequency controller, but now for these new time-varying dynamics that I'll introduce in a couple of slides. And these new dynamics that we're proposing do capture how inertia changes over time. So we can have controllers that are robust to that time-varying aspect, given that we're not working anymore with a linear system. And then the next part of the contribution is that we are aware that information entails a cost because we need to sense the information and then we need to broadcast it. So designing sparse controllers, basically that require low amount of information, it's something that we do desire in power systems. So with that work and motivation, we're able to propose a framework that has safety guaranteed when you're learning a controller in the context of frequency regulation. So we're able to design a sparse and guaranteed stable time-varying frequency controller for the new time-varying power dynamics. And we also test the improvement in the performance of that controller and in the stability as we introduce more features for the controller to use or have the controller have more access to information. So we can understand that trade-off of having more information and performance and stability or having less information and how that affects our performance. So with that, let's talk about how we're modeling now our power dynamics. So now we're moving away from having this linear system that I introduced with the swing equation, and we're modeling our system as a switch-affine hybrid system. So the aspect of the model that's the time varying are the inertia coefficients in this case. And we're assuming that we have a set of discrete modes for simplicity. So now we're going away from this linear system paradigm that we had before renewables into this switch-affine hybrid system that we're proposing. So here we see the state space representation. And in theta, we have, it's a vector with the phase angles in the different nodes that we have in our network. And then omega, it's also a vector that has the frequency at each of the nodes in our network. So basically, our omega is the derivative of theta. And then this matrix M, it's a diagonal matrix that has in the diagonal the different inertia coefficients, and they change over time. So that's why they're a function of time. And then our matrix L is just the Laplacian of our network. And D, it's a matrix as well that's representing the group control in our network. And over here, we see this delta, which basically would be the mismatch between the power injected and the demand. And U, it's a control action that we want to design. So then classically using matrices A and B, they're going to be time varying because of the inertia changes over time. So this would be our matrix A, our matrix B. And we are using one hybrid mode per inertia regime. So going from low inertia as low as 0.5 seconds, for example, all the way to a high inertia of 9 seconds. So we let inertia change over time in our simulations, and we design a controller that would be able to bring frequency back to the nominal point, regardless of how the inertia evolves throughout the day, for example. So now, formally talking about the problem formulation. So we're modeling power dynamics as this hybrid system, and we use a zero order Hall discretization. And now we're representing with X, the vector of the discretized angles and frequencies. And what we do with this, we generate a training set from just solving the MPC for this frequency regulation problem. So here, given that X, it's measuring the deviation from the nominal points for the phase angles and for frequency, we want to minimize the deviation. So we want to minimize this quadratic expression because we want it always to be as close to 0 as possible. And we're also minimizing the usage of our control action because we want to use the control action the least amount possible in a way that we're minimizing cost, for example. Because our control action would be power injection or power absorption if we have a battery, for example. And depending on what's happening with our demand, of course. So we can always match our supply with our demand. And then the constraints are the dynamics of our system. So we have an initial condition for the states where our frequency is starting and where our phase angles are starting. And then we have basically the dynamics of our system. And here we're working in discrete time. So here we can capture how our states are going to be changing given that we have a certain initial condition and we assume the initial condition to be removed from the nominal point. So we start in a safety critical operational point of the frequency being deviated by a certain amount. So then by solving this MPC, we can realize what will be the optimal control action U. So we could bring our frequency deviation back to 0. So then from solving that training set, now what we want to do is we want to now fit a controller via learning. Because in reality, in frequency regulation, the dynamics are so fast that we cannot implement a real-time MPC to try to control that type of problem. So this is just for training, creating the training data set. So the objective of our controller is that we want to learn a controller in a way that we are enhancing sparsity so that it doesn't require as much information from the network. And we want to understand to what extent communication between the nodes can be restricted, and we can still be able to design a stable frequency controller. So meaning, do we need to have information from, let's say, the nearest 3 nodes around us, or do we need to have more information and the nearest, I don't know, 5 or 10 nodes, depending on our topology? So that question we explored. So then to understand that, the strategy that we use, we create this optimal training set from solving the MPC that I just showed. So then from that MPC, we get optimal pairs of states and control action for a set of different scenarios S. And these scenarios are basically capturing different trajectories for our inertia. So in different ways in which matrices A and B from the dynamical system can change. In a way that it's rich enough so you can capture a wide variety of possible evolutions of the inertia in a system. And this scenario S, it's also capturing different initial conditions for our system. So basically different critical operational points where our frequency was deviated by a certain amount of hertz, for instance. And so we can be able to learn what to do in that critical case so we can go back to the nominal point. So then using this training set, we can learn, or we can try to fit a controller that is linear on the states. And to do this, we use a lasso regression for each node I in our network. And we assume that each node can have its own independent controller. So that's why we're indexing it by I, the node, and then it's a function of time. And we're assuming or hoping to fit a controller that would be linear on the states of the entire system. So we're trying to find this vector beta BI, that we are going to have a specific vector for every node I that we have. So a specific controller per node. And this vector is constant. So we're trying to learn a controller that has a very simple characteristic. So it's very easy to implement, as opposed to have like a time varying controller where the coefficients or the gains could change over time. We were hoping to find something that would be a little more simple, so it would be easier to implement from the practical perspective. So here we're just posting the lasso minimization, where we're trying to fit from these optimal pairs that we obtained from the training set from solving the MPC. So we have optimal control action, we have optimal state, and what we're trying to find is this vector beta for all the nodes I, and we're penalizing the components of the vector beta by using the one norm on it. And then we're penalizing with a certain weight lambda. And we're using the one norm because this gives a binary behavior for the resulting beta where the components are either going to be non-zero or 0. So it's not the case, for example, if we would have used the 2 norm. In that case, the 2 norm doesn't have that binary behavior. So you would have some components in the vector beta that could be like 0.03. So with that type of number so close to 0, it's not as helpful because we want to be forcing to use the least amount of information. So we want to penalize the one norm so we can have a more binary behavior from the controller beta, meaning that in some cases, we're going to have, let's say, 5 non-zero components in beta, and they're going to be not close to 0. And then for other components, we're going to get exactly 0. And then after fitting this linear controller, we add virtual inertia, which is a control proportional to the derivative of the frequency, as we've done in our previous work. So now looking at the case study that we used this 12-pass 3D region network that we've used in previous work, and also in some other work looking at low inertia systems. The community has been using this case study, so we use the same to try to see how our results relate to other work. So first we create the training set where we get optimal states and optimal control actions from the MPC. And here are the parameters that we use for the simulations. And then for each scenario, we are randomly drawing an initial condition for the frequency deviation with a normal distribution with mean 0 and standard deviation 1.3 Hertz. So this is rather aggressive in terms of frequency deviation. And then we simulate 400 scenarios to be able to capture a rich enough data set on how the inertia could change in the system. Then we assume that to be exogenous. We're not modeling that. That's happening also randomly. And also so we can have a rich set for initial conditions of frequency deviated. So with this, we're trying to use this concept of persistent excitation by trying to have more cases or a rich training set of different conditions that we could be facing. And now in the part of learning the controllers, so we're optimizing the lasso regression and we're using 100 possible values for the regularization parameter lambda. That's basically penalizing how many components cannot be 0 in our vector beta. And we use a tenfold cross-validation so we can get robust results. And then from that experiment, for our analysis, we choose a subset of controllers. Specifically, we choose this controller by the number of features that they're using. So we use the case of when you only are using 4 input features in your controller, when you're only using 5, then 6, 10, all the way up to using all the 22 states that we have in our network. And these 22 states come from the fact that we have a network that gets simplified to an 11-node network. And then each node has 2 states, the phase angle and the frequency, as I was mentioning before. And then to all the learned controllers, we add virtual inertia as in our previous work. And this goes in hand with the concept of trying to avoid negative side effects. And I'm going to get in a little more details on this one as we go through the analysis of the results. So looking at the mean square error for these different controllers using different number of features, we can see that when we go from having 10 features or more, the error doesn't change very much. So that could be saying that we don't need to use more than 10 features because then the error doesn't improve from when we're trying to fit this linear controller. While on the other hand, when we're using between 4 and 6 features, we do see that having more information or more features that the controller has access to does decrease the error in fitting that linear controller. And now we're doing this, or we're fitting this controller for a dynamical system. So we need to look at stability to see what's happening and to make sure that we're using a good controller for our dynamics. So after we fitted these controllers, we were able to realize that all the controllers in all the inertia modes were stable, except for the controller that was using only 4 features. So in this figure, we're looking at the eigenvalues of the closed loop system for a particular case of 9 seconds of inertia. And we calculate the closed loop system and we take the eigenvalues. And then in the y-axis, we're looking at the imaginary part of the eigenvalues. And on the x-axis, the real part of the eigenvalues. So here we're labeling with the different symbols and colors, the different controllers going from the controller that only uses 4 features all the way to the controller that uses 22 features. And to guarantee or to have stability in a linear system, we need to have the real part of the eigenvalues on the left-hand side of the plane. So basically negative real numbers. And all of them are on that side except the controller with 4 features where it has some values that are positive. So the system's not stable in that case. But that being said, we're working with a switch-affine hybrid system. So now we need to understand stability for the hybrid system under any possible switching. And we know that for a switch-affine hybrid system, even if all the modes are stable independently, there could be a switching sequence that could bring instability into the hybrid system. So now we need to use a different set of tools or a different framework to assess stability for the hybrid system. So for that, we use the Lyapunov approach. So we're trying to find a common Lyapunov function that ensures global asymptotic stability. And basically we can do that by solving this convex optimization problem, where in these constraints, we're forcing the matrix P to be positive definite. So it complies with being a proper Lyapunov function. And then this matrix over here, this is the Lie derivative of a Lyapunov function, and we're forcing it to be negative definite. So in the end, if we are able to find a positive R, this P would be positive definite. And if we're able to find a positive T, this derivative of the Lyapunov function would be negative definite. We will be able to say that we are stable. So basically global asymptotic stability we would be guaranteeing. So here's just written what I was saying. Positive R forces P positive definite, and then positive T, the derivative negative definite. So we will be able to guarantee global asymptotic stability of the system. So now let's see what happened numerically with the dynamics that we had and with the controllers that we designed, which all that's captured in this matrix ACL for the closed loop. And this constraint is for all the modes of inertia that we have. So we can find a unique Lyapunov function for all the modes that we have. So a unique P. So in this case, we were able to realize that the controllers with only 10 features or more do achieve this global asymptotic stability, but we cannot say the same for the ones that had less than 10 features. So even though the controllers with 6 or 5 features were showing a good performance and they were achieving stability on every inertia mode independently, they were not able to show global asymptotic stability when we're thinking of the hybrid system as a whole. So we need at least 10 features to truly guarantee stability in this type of system. So by doing this, this check with the Lyapunov condition, we are again stressing the concept of how we can avoid these negative side effects that if we don't check for stability, we would not be able to guarantee anything. But with this, now we're leveraging the power of data-driven techniques, but also using the classical approach from control theory to guarantee stability. So for conclusions of this case study, we were able to reduce the number of features in the controller all the way to 5 in our case study without impacting the performance and stability for any fixed inertia. And then increasing information beyond the 10 features did not enhance performance or stability metrics. And we showed that using at least 10 features was necessary for global asymptotic stability. So in this case study, we were showcasing how to avoid negative side effects by guaranteeing stability and how to design a training set that was going to have persistent excitation so it could be robust in the case of critical states. So now moving into the guidelines on how we can address this safety risk, not only from the case study, but more broadly speaking. In the case study, we see the example of 2 of them. So there's a lot of work at the intersection or in the question of, do we want to do offline training or online learning? So online learning can definitely help us in having a more sophisticated behavior. However, if we just use the classical approaches, they lack safety guarantees. Although now there has been some work that's addressing how we can embed these guarantees in the online learning. And then offline methods may be a method that's a little easier for us to start embedding these safety guarantees that we require, either a priori of or during our training or after the fact. And hybrid modeling, it's also something that's becoming very popular, where we do basically incorporate the physics of the system and also the safety constraint as early as the training is happening. And another technique that we can use to prevent this safety risk is variable partitioning. So this one is basically a way to characterize our state variables in our system in such a way that we split them in 2 different groups, and separating one group that would create problems if we use them as input features and another group that would not create any problems. So for this example or an example on how we can do that, refer to the paper, because in that one we looked at this challenge of the policy shifting and how we can wisely choose what input features to use from our own states so we don't incorporate more challenges. And then another topic that's been very popular in the last 5 years or so, it's safe learning. So for safe learning, there are different ways in which we can implement this. One idea would be to first identify the unsafe set of states and control actions that we want to avoid. So we pre-calculate that offline so basically where we don't want to be. And then we construct a safety controller based on that, for example, using reachability. And based on that, we can go switching between being in the learning or exploration mode. And as we get close to this boundary of the unsafe set of control actions and states, we can now shift to the safety control that we design a priori. So we don't need to, or we can avoid getting into that unsafe set. But we can still leverage the benefits of online learning when we're not in the unsafe case scenario. And the other approach that's very popular and I think has a lot of promise is when we embed these stability guarantees already in the training or adapt the controller after the training, as I showed in the case study, for example. And in the case of power systems, again, given that we're working with existing infrastructure, we should be designing controllers that are interpretable and also that have few input variables. And that makes it easier from the perspective of now interacting with the system operators, for example, because if our controller, you can interpret it and it's not a black box approach, then we can have more trust from the operators and from the expertise that exists around power systems and the people who have been working with this, rather than if we bring a black box approach that's brings much more risk because less analysis could be done from an analytical perspective. And the same, if we have to use fewer variables, that's definitely desirable. So we have a less intricate controller that's simpler to analyze and simpler to implement, given that we're working with this cyber physical system that's already in place for several decades. And in terms of empirical tests, definitely we need to be looking at the worst case scenario and even taking it further as adversarial testing. So we want to make sure that our controllers are robust. And we need to be mindful on how we're generating the data on what I talked about at the beginning of the talk, how we can use historical data and how we can use simulated data and how to get the best of both worlds and how to think about what would happen if we're being biased in the training data that we're using, how we can approach that from the controller design perspective. So with that, I would like to acknowledge my collaborators. With them, we proposed this framework and we have been collaborating since as well. And last but not least, if you know of people who are looking for a PhD, definitely send them my way. I'm in the space of recruiting. So I would love if you can help spread the word. We're also we're holding a workshop on how to apply to PhD programs. So if you have people in mind that would love to learn more, send them my way. And if you have any questions, I'll be happy to take them now. Thank you.